All right, so we have found the area of just one polar region. Now what we want to do is consider two different polar regions and find the area where they're overlapping each other. So in the picture you can see they kind of shaded it in for half of it, but technically what we're finding is this half as well, and I'll explain in a little bit why they only shaded half of it. So that's what we're trying to find. So the first thing we're going to do is let's go ahead and figure out what these intervals would be so we know where to look for answers. So we have a circle right here, and the interval for a circle is from 0 to pi. This is a cardioid, and the interval for a cardioid is from 0 to 2 pi. So I'm going to go ahead and show you just to make sure that that makes sense. So we're going to hit the mode button, and we're going to look at polar. We're looking at polar, so we're going to put our calculator into polar. And then for the window, I'm going to go ahead and kind of make my window match this. So first I'm going to go from 0 to pi just because I want to show you that circle. Go ahead and leave the step like that. For x, this is 6, so I'm just going to go a little bit further to -7. I'll go over to +2, and then down I'll go maybe -4 and +4, just so I can see kind of the same scale that this is. So my circle is -6 cos theta. And when I graphed it from 0 to pi, you could see that my circle is there. Now if I change my window, because to me this looked a little bit more like it was from pi halves to 3 pi halves. So if I change it, pi half to 3 pi halves, I still see the circle. So if I choose any interval that is an amount of pi, I'm always going to see that full circle there. Okay, so it doesn't matter where the orientation of the circle is, it just matters that we have that amount of the period, and then we can actually see the whole circle. So 0 to pi is going to show me that one. To see the cardioid, I'm going to have to do 0 to 2 pi. So if I leave it as 0 to pi, I see part of the cardioid but not the whole thing. For me to see the rest of it, I need to go from 0 to 2 pi. And I guess I didn't have 0 to pi, I had pi halves to 3 pi halves. So there's our circle, there's the cardioid. So what we're trying to do is just find this like funky oval shape that is the overlap of the two. So the first step in the process, and they already wrote the values down, but we're still going to do it by hand. The first step in the process is to find the intersection. Sorry about that. We want to find the intersection of the two graphs. So to find the intersection, I'm going to set the two equations equal to each other. And so I'm going to go ahead and take that 2 cos theta and add it to the other side. And then I'll go ahead and divide by -4. So 2 divided by -4 is -1/2. And then since I need to think of the interval from 0 to 2 pi so that I can include everything for that cardioid, I'm going to go ahead and find the thetas that are from 0 to 2 pi. So on the unit circle, we have an x-coordinate of -1/2 at 2 pi thirds and 4 pi thirds. And then once you find this part in the problem, what you need to do next is draw the lines and determine which line represents each region. So that doesn't quite make sense yet, but I'll tell you what I'm thinking about. So you can see they drew these dotted lines for 2 pi thirds and for 4 pi thirds. So we know that when we find the area of something, it kind of makes like a sector. So let's say if I did the sector from like 0 pi to 2 pi thirds, if I did that sector of the cardioid, then I would get all of this space right here, and I don't want that. That's not the area between the two. That would just be like the area of that part of the cardioid, so that's not what I want. So I have to think about what could give me just this little sliver right here, and that's not the cardioid. That's going to be just using the circle. If I look at the circle, then I can get just the area between the two. If I looked at that interval for the cardioid, I'd have too much area. So I'm going to think about which graph I want to use on that interval so that I get the inside of the overlap and not like including some of the parts of the outside of the overlap, so I'm getting too big of an area. So for the circle, we're going to go ahead and use pi halves to 2 pi thirds, and we're going to do that because it's going to give us this sliver right here. I colored that in, but you can't even see it. All right, so we're going to say the circle is from pi halves to 2 pi thirds, because it's going to give us that sliver. And then down here you can see that the other sliver would be from 4 pi thirds to 3 pi halves. You'll be able to see this one better. So if I use the circle, then I can get the areas of those two slivers. All right, so for the cardioid, I'm going to use from 2 pi thirds to 4 pi thirds. And you can kind of see that I would not want to use the circle for that, because if I used the circle, it would get this area and this area, yes, but it would also include all of this, and that's not part of the overlap. So if I use the cardioid for that interval, then it's going to give me the sector of just this shaded part, which is exactly what I want. So for the cardioid, I'm going to use the 2 pi thirds to 4 pi thirds. Okay, so we'll go ahead and we'll use our area. So I'm going to say, or our area formula, I'm going to say 1/2, and then for this little sliver, I'm going to say pi halves to 2 pi thirds of -6 cos theta squared d theta. And that's going to give us one little sliver. Now these slivers are definitely going to be symmetric to each other. I can see that this graph has a lot of symmetry. So I could say 1/2 this sliver, and then I could write 1/2 plus the other sliver if I wanted, or I could put a 2 in front of this and just say I'm going to multiply those slivers by 2. So what I'm going to go ahead and do is I'm going to add the other sliver, but I'm going to rewrite this problem showing you how to use the symmetry to get the area. So this would be 4 pi thirds to 3 pi halves, -6 cos theta squared d theta. So we have one sliver plus the other sliver plus, and then the whole area from the cardioid would be 1/2, 2 pi thirds to 4 pi thirds of 2 minus 2 cos theta squared d theta. Okay, so that's one way you could find the area. That's us writing out all the information for the entire thing. The other way you could write out the area is, and this is why they shaded only half of it, so I'm going to erase this. You can use the symmetry to your advantage. So you could say, let me find the area of one little sliver and this part, and then I'll just take that whole thing and multiply it by 2. So again, we said that one little sliver is pi halves to 2 pi thirds. And then the cardioid is this whole thing, but we could also kind of break it up right here. And we could say if we use 2 pi thirds to pi of the cardioid, that would be just this shaded region right here. So if I type that 2 pi thirds to pi, and so what I'm going to do is that's the shaded region that you can see right here, and if I want the whole thing, I'm just going to double that. All right, now I don't want to plug this in twice while you're watching. So what I did is I just plugged in this part right here, like that whole thing, showing all the 3 different pieces to find the 3 areas. So that's one method of plugging it in. The second is to plug it in the way that I just said. So I'm going to go ahead and type that so you can see it. So, and if you have a calculator at home, you should do it with me. So 2 times 1/2, and then we have pi halves to 2 pi thirds of negative cos theta squared. So you'll make sure to have those extra set of parentheses so you're showing that whole thing as being squared. And then plus 1/2 2 pi thirds 2 pi, 2 minus 2 cos theta squared. I hope I don't have any typos. That would be unfortunate. Dang it. I don't know if you guys saw where my typo was, but I just paused the video and typed in what I thought was the exact same thing. I must have missed something somewhere, but when I typed it in again, I got the right answer. So hopefully you guys got it the first time. So my point was that you should be able to do it both ways and get the same answer, as long as you don't have a typo. Okay, so we're going to do the next problem. Same thing, so I'm going to go ahead and set my window. I do have a circle, which I know is from 0 to pi, but my cardioid is 0 to 2 pi, so I'm going to go ahead and leave that interval there. For x, it looks like -2 to 2 is big enough for the picture, and -1, 2, we'll just do 3. I need to plug in the new equation. Okay, so we have 3 sine theta and 1 plus sine theta. There we go, so we have the whole picture. And so let's go ahead and set them equal to each other. So this is going to be very similar to the problem we just did because we have the same two shapes. Of course, they're not always going to be a circle and a cardioid. It's going to switch, but all right, so I'll minus the sign to the other side and divide the 2 over. And so theta equals pi 6, which I can see is this one right here. And then theta also equals 5 pi 6, which I can see over here. That was a pretty good straight line. All right, so pi over 6, 5 pi over 6. And then just like before, I have to think about, this is my overlapping region right here, so I have to think about, do I want to use the cardioid to get that, or do I want to use the circle to get that? So I can see that I should not use the cardioid, because even if I try to use from 0 to pi 6, the cardioid would give me all this area right here, and that's not what I want. So that means I'm going to use the circle from 0 to pi over 6. And then I'm going to go ahead and use the circle from 5 pi 6 to pi. And then that means that I'm going to use the cardioid from pi 6 to 5 pi 6. And the reason I'm using the cardioid is that if I use the circle is going to give me all of this. And that's not what I want. I want just this inner part right here. And so if I use the interval from pi 6 to 5 pi 6 of the cardioid, that's going to give me that. Okay, so when you write this out on your paper, you can set it up however you want to. I'm going to go ahead and find just half the area and then double it. So I'm going to say 2, and then I've got 1/2 of my sliver. And then 1/2, and then I'm going to go from pi 6 to pi halves. Okay, and I'm going to type this very carefully so I don't make a mistake again. Okay, so 2 times 1/2, 0 to pi 6, 3 sine theta squared, plus 1/2 pi 6 to pi halves, 1 plus sine theta squared. I got the right answer that time. Woohoo! 3.927. So regardless of how you wrote it, if you did this where you found half the picture and doubled it, or if you looked at all of the three pieces, you should have gotten the same answer. Okay, let's look at one that has different equations. So these ones are limacons, limosons, lima, whatever. So let's go ahead and graph this. We've got from 0 to 2 pi. And I'm going to go ahead and change my window to kind of be this big. So 0 to 2 pi, go left to 10, go right to maybe 7 or 8, go down to 10, go up to maybe 7 or 8. And I want to figure out which one is which, and so I'm going to go ahead and just graph one of these first. Okay, so that is this one. The fact that the screen is not square really messes with me. But you can see it's kind of going this way. And so this one is 5 minus 3 cos theta. And then that means that this other one is the 5 minus 3 sine theta. And so we are going to do the same steps. I'll go ahead and write 0 to 2 pi. I didn't write it for the last one either, but we could go ahead and, just if you ever look back at your notes, 0 to pi for that one, 0 to 2 pi for this one. Sometimes it's nice to have that stuff written down when you look back at your notes. Okay. So first I'm going to find the intersection between the two. I'm going to set them equal to each other to do that. So I can minus the 5 on each side. I can divide by negative 3 on each side. And so this means that I'm looking, of course you can solve this by getting the sine and the cos to be the same, but it's not worth the trouble. So instead, I like to think of this kind of intuitively, as like if I picture the unit circle where the x-coordinate and the y-coordinate are identical to each other. And that happens in two places. It's at pi fourths and 5 pi fourths, which totally makes sense if you look at this, right? There's pi fourths. There's 5 pi fourths. They happen to be the same line. All right, now when I printed this with a different printer, these were two different shades of black. It was like black and gray, but you can't really see that here. So what I'm going to do is I'm going to trace that first one with a marker so we can clearly see which one is which. Okay, that's a little bit easier. So what I want to think about is which interval to use for the 5 minus 3 cos theta and which interval to use for 5 minus 3 sine theta. So if I start at the pi fourths right here and I start sweeping out and getting that sector area, I don't want it to be the pink because if I start sweeping out with the pink, it's going to give me all of that stuff. So what I want is I want that when I sweep out that sector area, I want it to give me just the one from the black one because then it would give me this part. And so that means that if I use from pi fourths to 5 pi fourths, I'm going to use the black one, which is the 5 minus 3 sine theta. All right, and so that means for the second one, 5 minus 3 cos theta, I'm going to be sweeping out from 5 pi fourths, and I can't really say 5 pi fourths to pi fourths because that's a weird way to think of it. Those like don't go in order. So I could say from 5 pi fourths to 9 pi fourths because those on like an interval would actually be in order. Or, to get that same interval, if you wanted to use a positive pi fourths, you could say negative 3 pi fourths to positive pi fourths. So either of those would work. So if I wanted to write the area for this inside region and the whole region that I'm looking at is this right here, this like Kind of looks like a lemon. That's what I want. So the area is going to be 1/2 of pi fourths to 5 pi fourths, and that's 5 minus 3 sine theta squared d theta plus 1/2, and then I can use either of those. It doesn't matter which one. If you don't believe me, you can type everything in and make sure they're the same. So that's one way you could write the area, or you could use symmetry to your advantage, and you could just find this one because that was the easier one to write the interval for anyway. And then you could just double it, and that would give you the whole area. So you could say area is 2 times 1/2, and then the pi fourths, 5 pi fourths, 5 minus 3 sine theta squared d theta. Whichever way you plug it in, you should get 50.251. And I would recommend you plugging that in to see if that really works or not. Okay. I'm just going to kind of go through the other part of the notes, goes rather quickly. So to find the arc length of a polar region, it's going to remind you of the arc length formula that we've looked at already in other contexts. So the formula is r squared, so that's the original equation, r squared plus r prime squared d theta. And this r prime right here is not dy dx. This r prime right here is dr d theta. So you don't even have to do that much work to get to the arc length. So here we have a cardioid, so we know our interval is from 0 to 2 pi. We need to have the r, and we need to have the r prime to find the arc length. So r prime would be 0 plus negative sine theta. And so the arc length is from 0 to 2 pi. 1 plus cos theta squared plus, so there's my r squared, plus my r prime squared d theta. And if you plug that in, you get 8. All right. And then last section is the surface area of a polar region. So I do want to relate this back to what you've learned before. So I want you to recall that the surface area of a curve is 2 pi, and then the interval from A to B. And then the way that we kind of wrote the formula, as we said, it was the distance to the axis that you were rotating around multiplied by the arc length. And this part right here, to figure out the distance to the axis, if you were rotating about the x-axis, then the distance was y, so it was at whatever the function was, y equals something, and we would plug the function in right there. If we were rotating about the y-axis, then the distance to the y-axis was the x value. So it's interesting because it's actually the same in polar. All right, so if we are rotating around the polar axis, then the surface area is 2 pi, and we're going to go from alpha to beta of r sine theta times the square root of r squared plus r prime squared d theta. And r sine theta really is y, and the polar axis is the x-axis. So for the x-axis, the distance is y. For theta equals pi halves, which you can think of as the vertical axis, the surface area is 2 pi from alpha to beta times r cos theta, which we know is x, and then times the arc length. Okay, So if we look at this next example, we have a circle, and we know that the surface area, or not surface area, we know that the interval for a circle is from 0 to pi. And I like this one because when you like rotate it around the line theta equals pi halves, or that vertical axis, it makes a donut, which I really like. All right, so we have that. We also need to know what r prime is, and r prime would be negative sine theta. And so for surface area, we're going to say 2 pi from 0 to pi, and then we have r times cos theta. R is cos theta, so there's your r times cos theta, times the arc length. So cos theta squared plus negative sine theta squared d theta. And you can just go ahead and plug that straight in, and you end up getting that your answer is 9.870. And of course, this one is actually one that would not be too bad to do by hand. And the reason for that is that over here you have cos squared plus sine squared. When you simplify it, that equals 1. So this one, you really would just be integrating cos squared. And if we remember our power reducing formulas, this problem would not have been too bad to do by hand. So keep that in mind that we did all these in the calculator in the notes, but technically some of these would be fair to require you to do them by hand because you do have that skill after taking a class this long.